book.
Yeah.
You know, the Washington et al. This is here. So, you know, just give you a little bit of background. I think I may have told some of you in the class that Simon and I first met at the University of California, Davis, when he was doing his doctoral work. And I was on sabbatical there. And actually, my wife was getting a master's degree, so they were in classes together with, you know, my wife and Simon. And Simon, when I was at Davis, I taught that introductory statistical and econometric methods course. I think it was called the analytic method back then. And there were just like 6 students, and Simon was one, Mohammed Abdalati at UCF. It was an incredible cohort of you know, future safety researchers and, you know, successful academic people. So since that time, Simon and I have been in touch many times over the years. He's been at several universities, starting at Georgia Tech, and then Arizona State, Berkeley, and then Queensland University of Technology for quite a few years. Yep. And then just recently, he became the head of civil engineering at the University of Queensland. I guess it's been a year and a half now, 2 years?
2 years.
Oh, who's counting? But, and, you know, Simon and I, you know, over the years, we've taught short courses and we visited. Last night we went to Burn's Steakhouse, which we highly recommend.
Amazing.
So, you know, we did doing some of the touristy things in Tampa. But, you know, I don't want to do, some people were expecting an Australian accent. But, you know, he is actually, you know, an American, but he does say mate and a couple other things that are like Australian. Barbie, you know, Barbie, I don't know if I heard you say Barbie, but you do the mate thing.
Mate.
Yeah, okay.
In 9 years, that's all I can say.
But anyway, so we'd like to welcome Simon here, and I think he'll give a nice 1 hour long talk or so,
Yeah.
and, you know, should be in good shape. So thanks for coming.
Thank you, Fred. So I'll just start with a quick story about Fred as well. So, yeah, tip for tap. So, so I was a PhD student at Davis, and I was doing my you know, dissertation and going through all the process you go through as a PhD student. And Fred came down as on sabbatical, and if you remember, some of you are in that stage now, but I remember very fondly back to that stage of PhD. I'm trying to learn everything I possibly can about being an academic. I knew I wanted to be an academic, but I wasn't sure how I was going to get there, and I was trying to learn from as many people as I possibly could. And Fred popped into my life, into my PhD experience, and I thought, well, here's another guy I can learn from. And I remember I was taking this class and started to get to know Fred and asked Fred to serve on my committee, on my PhD, my panel, and so I was asking him. I went to his house one time to pick up some software. So he was renting an apartment down in Davis, and I went to pick up the software because we were using SST, I think, at that time. And I walked in, and I was sort of in this frame of mind, trying to understand this whole academic life, and here's this new person that I wanted to learn from. And I said, Fred, it just seems so hard to be an academic. It seems like you have to sell your soul and work weekends and work nights, and it's just such a hard path. And he looked at me and gave me some amazing advice. So I'm going to give it to you now. He said, no. He said, you have to work really hard when you're working. He said, but you have to have hobbies and you have to do things. And he proceeded to walk me into the second bedroom in the apartment. And it was lined with electric guitars along one entire wall. And he said, I play these, you know, guitars every night. And then we started talking about racing motorbikes, and I ended up racing cars. And anyway, it was a great life lesson from when I was very early in my career to say that, look, we don't have to sell our souls to do this job. You have to work hard, you have to be successful and do things while you're working and devote all of yourself to the job, but we don't have to sell our souls on the weekends and nights. And thank you, Fred, for that word of advice. And there's a lot of successful people who don't sell their souls and work really hard and are successful given that advice. All right, before I dive into the research real quick, I'm just going to give a very quick flavor of Queensland and Australia, and where I'm from, so you understand the context, because I'm guessing most of you have not been to Australia. How many people have been to Australia? So out of all of you, one person.
And I should mention, it's also the Sunshine State. And I thought we had that patented, but when you see the license plate, Queensland, the Sunshine State, so that's Florida.
Yeah, there's no lock on that one. So I'll just give you a brief shot, a snapshot. So this is how Australia is laid out, and we have 6 states in Australia. So think of Australia, the size of the continental United States, North America, but the population of 2/3 of the state of California. So to put it in perspective, so really in Australia, everyone lives, or the vast majority of people live on the coast. And so the coastal areas are filled with cities and population, and the interior is mostly outback, uninhabited territory, wilderness, amazing uninhabited territory. In fact, Australia, and impressions that you get in America are very different. That Australia is the most urbanized country in the world. And that is to say, more people live in urban areas in Australia than anywhere else. We also have this huge outback thing. So Brisbane is on the center of the East Coast. We're in the bottom of the state of Queensland, the Sunshine State. We're blessed. So Brisbane's the metro area is about 2 million people. We have 3 major universities in Brisbane metro area. In the city of Brisbane, there are actually 3 major universities. If you go out there, you get a couple more. And they're all PhD granting universities. We have Griffith University, Queensland University of Technology, and University of Queensland. And it's a river city. We have this big, massive river that comes through and empties out into the bay. It's a beautiful city, a very livable city. Probably in many respects, very similar in quality and climate to what you have here in Tampa. And we have, like you would have in Florida, world-class beaches to the north and south of Brisbane. This is the University of Queensland property. I actually get to take a ferry to work. So this river system, I live up here on the north side, and there are ferries that run. That's the ferry terminal that I would use to come in to work. And so I jump on a ferry and use my laptop and get to work. Or I take a bus. We just got the Lime scooters in the city. We have bike share, and one of the best bus rapid transit systems in the world. So I think we were just talking last night. We have 2,000 buses in Brisbane compared to 100 or something in Tampa. And the main things is we have these bus rapid transit systems that are dedicated right of way for buses that leave the city in all directions. And so they might go about 15 to 20 kilometers out of the city to the north, to the east and west, and to the south. So there's no traffic lights, nothing, so very high speed, competitive time-wise with auto travel leaving the city. So it's very, very highly, for a transport person and an urban planning person, it's a really interesting, vibrant city. UQ, we've got about 50,000 students. Rankings, everyone pays attention to rankings. I just got a few up here, but generally UQ is a top 50 university in the world, depending what ranking you look at. Some below 50, some just above 50, but generally we're a comprehensive university, have about 33 schools within the university. Civil engineering is one of those 33 schools. Civil in 2018 was ranked 12th in the world, so we have a fairly large program. And you can see at the bottom we have about 150 PhD students in civil engineering, 50 Masters of Engineering, Master of Science students, and about 750 undergraduate students in civil engineering. And these are the areas of work that we do, our subdisciplines within civil. And we have all of these represented in transport, we have 5 full-time ongoing academics in transport. So those of you who are thinking about doing a PhD and want to go to a different institution, I'd be happy to have a chat and lower master's degrees, or just doing research together. And we are blessed at UQ in Australia as being the most industry-engaged university in all of Australia, and these are just the industry partners for the School of Civil Engineering. So I put this together for an industry event that we had a couple of months ago, and we'd never actually put this together before, and we realized that we just had a tremendous set of industry partners, and including a bunch of global consulting firms, and a bunch of government agencies, and so we're very lucky. All right. Any questions before I leave that? I'm going to get into the research side. Any questions about Australia, University of Queensland?
Let's say you were partnered with DC Water.
Part of a what?
Let's say that the university has some partnership with DC Water, like from.
Is that one of the logos?
Yeah, and also the second from
DC Water.
Right
here.
The second
This
column,
one?
yeah.
Yeah. So, but I can't tell you what the nature of that relationship would be, because the way I put this together is I asked all my academic staff and so in the water. So if it was transport, I could tell you, but in the water area, I'm not exactly sure. If you were interested, I could follow up. But yeah. Okay. All right. So what I'm going to talk to you, I'm going to change gears and then get into some transport research. I'm going to give you just a brief introduction of why I'm doing what I'm working on. I'm going to walk you through a case study of some work we did in this area, and then where I think probably the most exciting bit is, and where it all leads to, is where we're going to go and where I expect to go with this research. Now, I have to say, I've been in an academic for 25 years now, and over that course of that time, you end up getting a sense of how important the research that you're doing is relative to all the opportunities you've had to do research. And I have to say, this is probably what I'm going to describe to you, in my view, is one of the most important opportunities in research that I've seen in safety in my lifetime working in this area. And I hope to convince you that's the case. I think we're at a crossroads where things can fundamentally change in safety, and they need to change. A lot of the work we do is incremental research, but I think this can lead to transformative research that will change a bunch of things. What I'm not saying is that what I'm doing is changing the world. What I am saying is that what I'm contributing to, I think, is a body of research by a number of researchers that I think is going to really potentially change what we're doing in safety. And I think it's very exciting. So I think a lot of people will be involved in this transformation. So we all understand the practical motivation. I won't go through this, but the number of people killed and injured, it's increasing in all developed countries, becoming higher and higher on the list of things that kill people. And in most developed countries, the number one killer of people under age 25 is getting involved in a motor vehicle crash. We were talking about, whether we had a discussion yesterday about whether we let our children skydive, and we said, it's a relatively risky activity, but still, if you're under 25, this is the number one. Driving and being in a motor vehicle is the number one killer of us. And so it's a huge problem. It's a huge problem in Australia. It's off the charts big problem in developing countries. It's a whole other area that we need to do a lot of work in, but in developed countries it's still an increasing problem, and it's one that we know is driving a lot of the investment in this area. From an academic, I think maybe this is the wrong presentation. I just gave you my USB and assumed that the right one got
Okay,
up.
is there another one?
Yeah. I think let's
see if we can load up.
No, that is it, so it just didn't,
Oh,
something.
up, sending it up to you.
Okay. All right. Okay. Interesting. Okay, there, just out of order. All right, so the academic motivation is that we know very little, and I'm going to talk a lot about and define these terms, but surrogate measures of safety. So things that we can observe that aren't crashes and injuries, but that might be precursors to those. So we call those just loosely for now surrogate measures, and we'll talk about those in more detail. But we don't know really what are those relationships between those and crashes. We've done very little work to understand that. And the work we have done, which started a few decades ago, came up with the conclusion that they're actually not one's not a reliable predictor of the other. So if I observe people illegally crossing a crosswalk, for example, that's not a reliable predictor of how many crashes, pedestrian crashes we would have at that location. So that research was largely abandoned until now, and they're revisiting it, but we have a whole bunch of new tools that can help us. So that this is the academic motivation for what we're doing. We have a moral dilemma, and it's something we actually don't talk about much. But as a research community, we have a problem now that is the road safety management practice all around the world relies on people to get injured and killed before we then know where to invest to prevent people from getting injured and killed. And it's a moral quandary that has plagued us in road safety for 40, 50 years. And we often, in standard practice, is we wait until let things operate for a substantial length of time, usually 2 or 3 years, before we see an emerging pattern of crashes and negative outcomes. Then we can say, now we can justify. In fact, the procedures in most DOTs require you to justify, given the cost of death and injury, an expenditure to then fix that. If that's not a moral dilemma, I don't know what is. So that's a pretty crappy place to be in trying to change and figure out how to solve things that people are required to die or be injured. So it's something we really have to fix. The other thing that's pressing on us, and this is not unique to the U.S., but the DOTs that make those investments want the quantitative information. They are not happy for myself or Fred or one of you to rock up and say, well, I think that intersection's not working well. Why don't you spend $5 million on it? And say, whoa, just your hunch, or is it your intuition? And show us the evidence that it's not working well. So all of the DOTs around in developed countries are requiring increasingly hard evidence to justify the expenditure, so benefit to cost ratios and all those sorts of things. So we're stuck in this sort of paradigm where we're so reliant on crashes. So why? Why are we reliant on these outcomes to assess safety? Well, they are the thing we're trying to fix. So it makes sense in a way that if we want to eliminate crashes, that we're focused on them and counting them. We want these repeatable quantitative linkages and relationships that to date have been lacking to be able to do other look at surrogate measures. And I hope to convince you today that we're at a point where that's going to change, and that is changing. So methods for reliably collecting surrogates have been lacking before now. So before now, in fact, many of us would have done this. I did this in my master's degree, stood by an intersection with a pad and made notes of what was happening at a location, recorded violations or observed behavior and write it down. It's just not reliable, it's not accurate, it's not precise enough. It's subjective, what we observe, we miss things, et cetera, et cetera. So those methods have not worked in general when we put them to a rigorous test and developing evidence. So the challenge is, I would suggest, that given this history and where we are, the moral quandary, that we need to develop a rigorous procedure for relating surrogate measures, things that we can observe that are easy to observe, that we know are reliable predictors of crashes. We need to quantify that, and we need to build a methodology around it. And I hope to convince you by the end of the presentation that we're at a really good point and able to do that now. So, what's the theory that would guide us? So the theory really that we have so far is best probably captured in this picture, is that if we put all of activity on the transport network into a pyramid of activity, and say at the very top of that pyramid, the very point, are those activities that represent crashes or injuries. So actual conflicts, not conflicts, but crashes between pedestrians and cyclists and motorists and public transport buses. It's a small fraction of all the activity that we see. Very small fraction. And we know that. Crashes are very rare events. And so people can drive 10, 15 years, 30 years without ever getting in a crash. So they're very rare. Just below those are events that we believe could be precursors to those other more serious events. So think, for example, two vehicles on a collision course that wait very, very long before one of them or both of them stop that collision. One of them brakes, one of them diverts, whatever. If we could measure that precisely, there might be a threshold above which we say, that threshold is a threshold by which we could reliably use that to predict crashes. Pedestrians and vehicles in the crosswalk, etc. So we'll talk about more of that in more detail. But the theory suggests that somewhere up in this area, there are things we could observe that would help us predict the things in this area. And I'll come back to that and look at more of a sampling problem in a few minutes. And then all the way down the bottom, we have normal everyday events that we still can observe, but they don't give us any clues to whether there's risk, undue risk on a site. The thing that's changed all this is that, and many of you would be aware of this, is that we've had huge advances in computer technology and computer vision. And not only that we can do it, but we're getting to the point where we can automate a lot of this stuff. So we can watch hours of video and have the computer process it very, very accurately. And I'll show you a couple of examples. And that's changed everything. And so now, and this is a depiction, we can track all kinds of vehicles. We can classify vehicles, we can count vehicles, and I'll talk you through a little bit of how advanced that technology is. And so I'll pause here and say that a lot of this work that I'm building on has been work developed by Professor Tarek Syed in the University of British Columbia, and he and I are still working on a lot of this together. He has done a lot of work in the video, or his team, his postdocs and his PhD students have done a lot of work in advancing this video analytics stuff and techniques so we can apply it to road safety. And he's been doing that for, as a major research team for probably 15 years now. And I was tracking his research through TRB and other means for a long, long time, and I'd sat through a bunch of presentations and I thought, this is still back where we were. There's still no meaningful relationships between these things and crashes. And eventually, and it was just about 5 years ago, he gave a presentation where he convinced me that finally we actually could develop some reliable relationships. And then I got on board and I said, Tarek, you've got it, you've nailed it, let's figure out how to advance it. And so it's still creeping along. There's still a lot of work to be done, but that's when things started to change. And it's just very quickly in the setup, you can even use things like Google Earth to get position locations, very little information required to set up the cameras. We can mount cameras at these locations, and then observe behavior, and I'm going to show you, walk you through what we're going to look at here. So these are different measures. I'm going to walk you through. This is distance to stop. This is gate time. This is time to collision. I'm going to spend most of my time talking about time to collision, and I'll define it and explain it. Up here we have vehicle speed and we have pedestrian speed. So this is input from a camera, and what you'll see. Anyone know how many frames per second a normal camera has?
30.
Yes, yeah, so it's roughly 30. So what you're seeing here is that the signature of a pedestrian is very different than the signature of a vehicle, because when we're measuring, a camera measures things at such a high rate, we can actually, and what it's showing us is that we actually accelerate and decelerate when we walk. Right, so it's not, we don't walk at a constant speed, we actually, as we take a step, accelerate and it slows down. We never know that. We think we walk at a constant rate. But this is indicative of the fact that the computer, without even knowing and seeing that pedestrian, based on that signature, can tell that it's a pedestrian. Interestingly, that signature for men and women is on average different. And with 90% accuracy, you can tell whether a pedestrian is a female or a male based on the frequency and the gait speed. Now, what I want you to focus on is that we've got a pedestrian in a vehicle going in a potential conflict, and what this is measuring is the time to collision, and I'll spend a little more time talking about that as we go through. But conceptually, what we're looking at here is if two objects are on a collision course, if we can measure accurately that they're on a collision course, and one of them realizes that if I don't change and manage this, I'm going to collide with that object. So I'm going to change direction or change my velocity. And at that point, they're no longer on a collision course. So if I project where they're going, their collision course has ended. So that time to collision, so that could happen in, say, 2 seconds. We're 2 seconds away from colliding. One of them is going to change direction. So now, all of a sudden, the shortest time to collision has been 2 seconds before one of them decided to divert. Well, we can measure that accurately. So think about time to collision of 1/10 of a second. Right? That's getting pretty critical to a crash. That's the very last 1/10 of a second before a crash was avoided. And a crash is when it's 0 seconds. So the computer can measure these interactions to very, very high degrees of accuracy. Let me show you another picture. This is a video. This is in China, the intersection of China. If you look at this picture, you'll realize why I made my statement that developing countries, it's a whole different ballgame. But the point here is that all I'm showing here is this truck and this pedestrian. And it's tracking their position at every moment and the distances, and we can calculate a whole bunch of metrics. I'll show you some of the things we can calculate in a minute. But the computer can actually track every single object pair in this scene. And think about someone with a notepad or whatever trying to observe. This is no possible way we could get accurate, detailed information. But the computer, we can set it up, and we do set it up, to look at every single pair, and we're calculating every moment which pairs are on collision courses and what metrics do we need to measure about those collision courses and what they're doing. So that is, if you look at that image and you think about the potential data stream you could get from just observing the intersection. And so I want you to start thinking about, in terms of research, how long do we need to observe that intersection for? And what kind of pattern do we need? Morning peak, weekend travel, et cetera, et cetera. Theoretically, we wouldn't need to observe it very long to try to understand patterns. The big question is, what patterns do we need to see and understand? So, just to expand your mind, here are just a number of things that computer can calculate for us very easily. Gap time, time lapse between the completion of an encroachment by turning vehicle and arrival time in the crossing. I'm not going to read all these to you. The encroachment time, the maximum deceleration rate. So when they are coming, What was the maximum deceleration we observed to avoid that crash? Clearly, someone slamming on the brakes might be indicative of a problem. And if that's happening a lot, we can measure how often that's happening and measure those sorts of things. So we can measure all kinds of things. This is just one short list. We've actually put, as part of this research, we've compiled a table and we've got about 30 different metrics so far that we can measure from the video analytics on precise movements and activity. And you can imagine trying to understand what we need to measure for a pedestrian and a vehicle collision might be different than two vehicles coming and having a head-on collision. You might want to measure different things as predictors or precursors of those events. So let's focus on time to collision a bit, and then I'm going to walk you through a case study, what we've done, and then I'm going to come back to where are we going. So the time to collision, if you think about it, gets tricky when we have turns. Because if we have a vehicle coming to an intersection making, say, a right turn or a left turn, and a pedestrian walking across, well, we have to actually predict where it's going to be in the future, which isn't on the trajectory, so it's on some trajectory. So the way we do that, and the way we've set that up, is that we know, if we observe the intersection for a little while, that if a vehicle is turning, once the nose of the vehicle turns a slight bit, we can say that vehicle is a turning vehicle, and all the vehicles that have turned from that point, the average or median vehicle follows this trajectory. And as long as they stay on that trajectory, that's the trajectory we would predict. And we know the speed, so we can say, so you'll, as you turn the corner, you'll hit the pedestrian. If they get off that trajectory, then we say, well, vehicles on this trajectory, the average turning radius was this. And so we can keep updating very, very rapidly our forecast for where vehicles are going to go in that intersection. So flashback to the Chinese intersection, we're predicting, as well as observing all that video, we're predicting where everyone's going based on all of the mapping we've done of the behavior at the site. So if I showed you a different image, we can plot lines for all of the vehicles as they come, and those lines represent a distribution of the trajectories that vehicles have taken, if they're turning, if they're going straight, if pedestrians are going across, etc. And so we calculate then a time to collision. So how close did they get to colliding before one of the two objects avoided, braked, sped up, whatever they did to no longer be on a collision course, and we can measure that, and we will. So we focus on time to collision, and I'm just going to walk you through a very short project we did, and the sort of more the practical side, and then we're going to come back to the research questions and how we're going to go on from here. So we looked at a site. We finished a study about 6 months ago for the Brisbane City Council, and I'm going to kind of go through it fast, but we had a very complex site. So they gave us 3 different sites, the very complex movements. We didn't have a before-after situation, and we'll talk about that. All we had was the site, and they said, this is complex, we have weird behavior here, tell us what we should do. We tell them to analyze it with your analytics. So we set up cameras at multiple locations around the site, 4 cameras, and then we hired mobile camera provider that would come up with and we had to get the right locations to put the camera so we didn't influence any behavior in any way, restrict any sight distances, etc. And we then set up these cameras. Here's how we set up the camera. So we only observed for 1 or 2 days, right? This is experimental. We might think about doing a week, but a week to observe and make safety. If we can do a week of observation and make some statements about safety and what we should do at a site, that is so much better than what we do now. We don't have a quantitative way to do that now. We usually have to wait years. So the video does counts, it does classifications, it does, you can program to say violations. So we can define the boundaries of a crosswalk, for example, and we can count how many pedestrians use it, and when they go outside the bounds of a crosswalk, we can say they're violating the crosswalk. We can actually sync it with the signal, so we can tell when they're violating the signal as well. And you can see the pedestrians per hour. We can get all kinds of information. And the reason I'm showing you this is I want to get your heads around the kinds of information you can get from this kind of analytics. And so what we've got the number of time to collisions less than 1 second. So how many objects were within that 0 to 1 second time frame. Okay, we can cut that down to any bin size we want. We didn't observe any crashes, by the way. We observed a lot of things that were very close. And we can calculate conflict rates and et cetera, lots of different things. We can look at conflicts by time of day and by volume as we measure conflicts as the time to collision below a certain threshold, for example. And we can look at what kinds of conflicts are happening, what user pairs are having conflicts, whether they're vehicle to vehicle, vehicle to bicycle, vehicle to pedestrian, etc. And we can develop heat maps. You can't see this very well. This is the intersection of the heat map applied. So we can see spatially where the conflicts are happening. So where those close calls are happening. When we showed the heat maps to the engineers who designed the sites, and said, this is where your conflicts are happening, they said, we had no idea. Said, that is amazing information. We have no idea that we've gone to the site to observe it, but when you observe a site for 10 minutes, you can't make sense of a site. And they were all flabbergasted about the depth and richness of information that you have just simply showing a heat map of where conflicts are occurring. Bear in mind, we haven't established that time to collision conflicts are related to crashes. But we're just making an assumption that they have. In fact, in this research, we just said we'll use small time to collision. They found in Canada that these are related to crashes, so we're going to make an assumption that they are. But there's a lot more work to be done there. But assuming that's true, we can see all kinds of heat maps about where the conflicts are happening. And then you can go in and diagnose. And we made a whole bunch of recommendations about what they should do at the intersection to deal with these conflicts. So you can get the violation rates. So look at the difference in violation rates across the crosswalks. So we've got one crosswalk where there almost 24% of the pedestrians using it are violating either the markings or the signal activation. And we got some crosswalks where the compliance is quite high. They didn't know, had no idea. Because the only way you'd know is if you stand down there and observe it for a period of time and collect the data, and you just don't do that. And then you can pull out information and you can see where things are going strange. So that person made a right turn from, this is the only lane that permits the right turn. And so you get the benefit of also seeing what's happening from a driver behavior perspective and the confusion that's happening and what's and all these things are tracked, right? All these close calls are tracked, so we can see what's happening there at the site. That's leading to these sorts of events. Again, no crashes occurred, but we're diagnosing the operations to try to give us insight about where crashes might occur if we just let this thing keep running. And again, the right lane is the only turn lane that can go over. So there we've got a pedestrian violating, and we've got a person turning from the wrong lane. So you can start to get insight about where the things are happening, and then go back and pull up the video. Here you have pedestrians violating, the operation of the sites grossly, and it gives you a lot of great insight. Okay. So, how we can take this and go further and transform road safety. I hope you have a sense of what's possible with this, but there's some hard work to be done. And I'm gonna, in the next few minutes, I'll talk about that and then I'll open up to questions. So how are we gonna do it? What do we still need to do? What we don't know is how reliable, what threshold do we need to look at? What do we need to understand about, for example, pedestrian vehicle conflicts? What do we need to measure that is the most reliable predictor of crashes that occur there? Is it the same in Canada as it is in Australia, as it would be in Florida? My guess is that every other study that's looked at safety and the transferability of results in safety suggests that results are rarely transferred. The driver behavior is sufficiently different that say the parameters in the model would be different in Florida than as it would be in Brisbane and in cities in Canada. And so we need to develop a process. So I'm just going to talk to you about what we're doing. So we've got another project funded by our transport agency, about $500,000, and what I'm going to talk to you about now is what we will be doing in this next project to develop this further. The idea is I'm going to talk you through a little bit of the technical stuff. So what we're dealing with here are minimums and maximums. The minimum time, all of those metrics I put up involve a minimum or maximum. And so we're dealing with what we call extreme value distribution. And those are very interesting. They have very interesting properties. And so we're just starting to look at the analytics of this process is that we need to relate these minimums and maximums, or the distributions of these minimums and maximums, to the events of interest for us, which are crashes. And so, for example, the minimum time to collision is a minimum, observed minimum of an event, and the distribution of those would be a distribution of minimums. And so, I'm going to come back to the problem we're looking at from an analytical standpoint. The argument would be, and the theory development would be, is that this is just a sampling problem. What we have now is that we have to wait to see a sample long enough. We have to wait a couple of years, 3 years, to see a sample long enough or big enough so we can get the events we're interested in. And what we've done now is said, we're going to sample for a lot smaller period of time. And what's going to happen is, if we sample long enough, we'll see the crashes. We'll see the time to collisions below 0. But if we sample for a much shorter period of time, we won't, or we're not likely to. But we will see the rest of the distribution. And we'll see the rest of the distribution. And so what we'll use is extreme value theory and distributions to fit this distribution and estimate, if we observe the sample longer, based on the evidence we have, how many time to collisions less than 0 would we have? And then we'll relate this estimate to the covariates and explore which covariates are the ones that matter. So essentially what we're going to do is collect the information we need about the surrogate measures and explore the parameter space, understanding that we've got an extreme value distribution, and we've got to recognize that. So it's essentially a distribution with very specific properties where we haven't sampled it long enough to estimate that tail. So we recognize that the tail is missing, and we might come up with a methodology that looks something like that. So for signalized intersections, for angle crashes, we need to measure time to collision, post-encroachment time, and maximum deceleration rate as surrogates with certain thresholds to predict the number of angle crashes at a site. And so what you can think of is that there's a whole set of equations that, because we know nothing about the theory, about what are the things we need to measure for angle crashes and rear end crashes in the surrogate measure space. And so, and this is all hypothetical because we haven't done the work yet, but and we might just have a different set of surrogate measures we will measure through the analytics to predict the rear end, sideswipe, vehicle head, vehicle bicycle crashes, how we want to classify and understand crashes and predict them. If you can imagine, if we had this, once we have this, We then can go to the intersection operators and say, let us observe your site for a day, and we can tell you where your crash risk is. And we can then diagnose and say what you need to do to fix and reduce crashes that have not yet occurred, but based on what we know will occur if you just let this intersection keep running. We've never been able to do that, and never been able to do it quantitatively anyway. And so the potential is huge. Intersections being where about 60% of all crashes occur. I would envision that we're going to end up having a series of equations where we're going to have to observe crashes. We're going to have to do the hard work and understand what the crash history was to make build these relationships. But it's going to be a function of a bunch of these surrogate measures and a bunch of properties of the intersection, the traffic and exposure. So how many vehicles are going through the intersection, and a set of covariates about the intersection, how many lanes, how many turn lanes, what's the signal phasing, et cetera, et cetera. We need to understand what other factors are affecting this process. And then the set will be a set of covariates, or the surrogate measures that we need to measure, and what parameters, what ones are important, and what ones are not important in looking at relationships. We could envision a very similar kind of set of equations that would look at the severity. So not just the number, predict the number of crashes, but which ones are going to be severe. And there might be a whole different set of surrogates that will help us predict severity of the crashes that occur at these locations. All right, I'm going to wrap up with technical challenges, and then I'll take questions. So one of the challenges we're going to have is that the temporal scales are very different. So we're going to measure a site maybe for 2 days, but then we're going to try to relate that to a crash history that might be over a 2 or 3 year period. So we've got this homogeneity question about, well, was the site resurfaced and pavement last year, and how does that, so we're going to have to work through that one, because there's a big underlying assumption that the intersection operation hasn't changed sufficiently as a result of other things over that crash history period, and that what you observe in a short period of time is reliable enough to relate to that longer history. So the timescale issue is one we haven't even begun to start to look at yet. But certainly we're going to have to check to make sure it has the signal has been operating in the intersection in the same way during the crash period, and there have been no major kinds of constructions. But that alone may not be enough to understand that. We need to spend more time on it. So that's going to be a big challenge. There's no theory yet on what are those relationships we need to look at. We don't understand that. We haven't done much work, so we'll spend a lot of time trying to articulate and explain why these are the metrics that matter for rear-end crashes, and these are the metrics that matter for pedestrian crashes and other things like that. So there's a bit of work in the theory development as well. So, roadmap of what we've done, where we're headed. I hope I've sold you on the idea or the notion that this actually could have a huge, huge impact on managing safety and fundamentally change the way we do things. But there's a bit of work ahead of us, and I think a lot of people will be and can be involved in this work, and it's very exciting work. So happy to take questions for the remainder of the time. Yeah.
So, two questions. Second one is maybe observation. But what was your take in terms of your algorithms to spot or identify instances of false positives and false negatives? Because it seems like the way you presented is 100% accurate. How do you deal with that?
It's a fantastic question, because I wouldn't have intended to portray it like it's 100% accurate and there's no false positives or negatives. But it's a great point, because a lot of the research we've done to date So a lot of this work is, for example, in the area of measuring activities and then trying to predict crashes that might occur at that location. They've been more proximity based. So, for example, if we observe this behavior at a site, then the crash risk is increased. But all of those studies have this huge false positive problem, and that we have this small increase in probability, but the probability increase is so tiny. It's significant, but it's so tiny that the vast majority of users and that go through the site are not going to experience a problem. The way we're trying to deal with that here is that we would relate the actual outcomes with the predictors, and we will be trying to work through and say which ones are the reliable predictors of. Let's say, let me try to get more specific. Let's say we go to a site and we had 10 pedestrian-involved collisions with motor vehicles. That's a fixed number. We will be looking for the evidence that tells us that if you measure these things, those are reliable predictors of those 10. And we'll have multiple sites, and so we would say, well, if it's reliable there, then we'll test it over here. If it's reliable here, it should be reliable here, and we'll have multiple sites. And so we will be ruling out the insignificance of that in predicting that count. The difference between those false positives is that I'm not trying to suggest that we're going to go out and say, observe this, oh, you're going to get a crash in the next 5 minutes. What we're using, because then you're going to have a whole bunch of, or you might have a crash. Well, which vehicle is it? It's not that one, it's not that. You're going to have a whole bunch of false positives. The intended use of this now is to say, if you keep operating the intersection in this fashion with this set of circumstances, over the next year you will probably see about 10 crashes occur. I don't know when, but on average, the model is going to predict for you how many of those events would have, and therefore, and you say, so well, and this is the particular event that you're trying to reduce, so let's put in a countermeasure to reduce that thing, that surrogate, and maybe get that prediction down to 5 or 3. So in our case study, as an example, you saw those vehicles coming across. We don't know which one, so we didn't observe any crashes. We have no idea when a crash between one of those cars into the side swipe might occur. But it's very likely it will. But we could see from the evidence that the vehicles needed better guidance coming through that intersection. And so the Brisbane City Council has come back in and restriped that intersection with better guidance. And so that behavior is no longer happening. And so we don't know which particular event is when it's going to happen. There'll be tons of false positives, but we're trying to get around that problem by saying this is the long-term risk. We don't know in any given week or day that it'll happen, but the long-term risk is X. So let's reduce the long-term risk because we know what relates to that. So that's. I don't think we'll have a false positive problem, like a lot of, because we're not trying to predict when it will occur. Then we would. Yeah.
Dr. Washington, it's very exciting to use video recognition in safety. I was aware of some applications in mobility, like NGC data, and recently we were working with FHWA, Turner Fairbank, on a project, basically flying some drones or helicopters to collect some trajectories for traffic simulation calibration purposes, not to the safety aspect.
Yeah.
We also are faced with some data error issues because video recognitions are not always 100% accurate. So we were actually recommended to, we plan to actually compare the video detected the trajectories with manually extracted trajectory by students, or we can hire some other graduate students to track those trajectories, and that may give some error. So I was just wondering if you can also measure this kind of error. I know actually actually the video technologies are a lot better. NGSIM data is probably not suitable for safety matters because errors are dramatic, especially for accelerations or high order information. And now, as the technology improves, there might be still some errors. But would it be possible to incorporate that kind of errors into your safety surrogate measures to instead of a value, you can give like confidence interval or distribution like that.
Yeah. Well, it's a good point. All of the techniques so far have been validated. So every step of the video development. So for example, when I said you could detect females versus male pedestrians with 90% accuracy, that was through a validation. So they ran the video, then they actually just did a manual count, women, men, and same with counts of vehicles, and so they validated, never had a validation less than 90% accuracy in anything. So that's kind of where it's sitting in terms of the precision of it. The inaccuracy comes from mainly not the video processing itself, but some of the video processing, but there's a number of issues that come up. You're trying to tell a video when things are two objects versus one, and there's a bunch of very delicate settings to say that that's actually one object, not two. So the errors there are you're calling one object two objects, you're calling two objects one object, and so those are the fine detail errors. The other ones are occlusion. So depending where your camera is, you might have a big truck and a car behind it, but you never see the car because the truck's too big and you just can't see it. So those kinds of things are contributing to the errors. So, but those errors would show up in the model in the error term in a sense as omitted effects, and we then could use that to estimate the certainty of our prediction. So absolutely, it's embedded in a sense in the data that we would get and trying to relate crashes to those certain measures. But that's where the accuracy sits, is around 90% for the video analysis.
Could you comment on if we are using this methodology to predict X many crashes for the certain location in the future years, compared to just the existing method, people pretty much are looking at the historical crashes and first, I think it will be very highly correlated with the location and the high volume of crashes and injuries in the past X many years will actually have a high prediction based on your model and approaches. And what would be the advantage of using this method versus historical data?
Okay, it's a great question. So I'll answer it by sharing. When I presented this to the chief engineer for the Brisbane transport or the Queensland transport main roads, and several other senior executives, and the differences, the fundamental difference between the historical record and what this happens, the engineers that work on the sites have no feedback about detailed operations, and so they were able to go in and say, this right here, this little 5 meter by 2 meter section of the intersection is where all the bad stuff's happening. And they didn't know that. And there was no way a historical record could tell you that. You know where they end up crashing, but it doesn't tell you about the operations. And so when they saw that, the engineers, they're saying, this could have feedback to design guidelines, and if we fix this intersection, because we know this, then we might then build that into our design guide and say, no intersection should have this kind of flawed design approach. That feedback loop to the safety is what we don't get at all when we look at that. So from an engineering operations standpoint, it's just a whole different ballgame. And so that was the thing that they said, this is unbelievably potentially huge for us if we can reliably say that this is. They actually don't even, the DOT, they can say, we don't even, it's the academic and me and all of us that cares about that relationship between crashes and the movements. They're convinced already. You show us things are almost colliding. That's terrible. And it's like, well, not so fast. Maybe that's not where we need to establish that relationship first. So that's where our interest lies. But if once we, and I'm convinced we can do that, then the whole gate opens up. And this is a whole new insight we've never had before. So it's totally, yeah.
I guess that segues kind of my thought, which was, you know, it's not as if the road budgets are increasing, but if you can access more, you can look at more intersections to see that there needs to be safety improvements. Do you see this as leading more to like more slight incremental changes to intersections for safety improvements, or will we still have to depend on, okay, well, there was a large number of accidents, a large number of injury or fatalities at this intersection, so we're going to fundamentally change this intersection? That
Yeah.
question makes sense.
Yeah. No, look, so I'll give you a short answer, but then if you want to talk about it after, but the most exciting bit of this is, well, I think it's all very exciting, but, and another exciting bit is that where does the product development go? And the product development part, which I didn't talk about, is if you think about using this in a real or semi-real time operation standpoint, you could say at certain times of day, there's risk that happens that isn't there at other times of day. And so maybe we at real time adapt the operation of the site to reduce the risk during those times of day where the risk is there. And we don't have the ability to do that now. So product development of real-time management is very, very exciting. That's where the DOT says, oh my God, as we go to these advanced controllers that can change the operation of a site based on some triggers that we couldn't do before, this opens up a whole new thing there. But the fundamental question is that the idea is that 60% of crashes in urban areas occur at intersections. So if, let's say, as just a rough number, if we could reduce 50% of those by proactively going out and identifying where so there'd be incremental changes to operations and site configurations, but in advance of waiting for all these collisions to occur. So we just have a much more quick, rapid response to, in the short-term development, the rapid response to the management of the sites. In the longer term, we could actually go to a more real-time management of sites that proactively responds to where the risk is.
Okay,
Yeah.
we're gonna have to keep everybody moving along, but Simon will be available to answer questions.
Yeah.
So thank you again.
Let's take a group photo.
Oh, yeah. Before people run out.
So what's the students have?